Right, so you've all got me again. So I'm going to report on a little piece of Schwartfeger's. He's been a bit under the weather this last couple of weeks, so I've taken over this role, and I'm doing a much worse job of it than he would. So I have to bear with me. It's not really my work. But this is system requirements modelling. So this is very similar to the work Richard was talking about, but transparent with seeing what will happen in the future. As we get the generation mix and the load mix changed, then is the system still fit for purpose? We're probably not quite at the stage they are at, where I'm just going to introduce the model and a little bit of hindcast verification of that to talk about some of the issues with that sort of model. So this is, I guess, the aim of any kind of dynamic programming model for this sort of scenario analysis is to develop this tool to test these scenarios to see if they can work, to see if what's needed, if the current system is, or what might be needed to make it fit the purpose. Of course, it's hugely about managing the peaks and troughs of generation and load and managing the mismatch between them. And of course, as Richard pointed out, hydro storage is a incredibly useful, in fact, an awesome resource to provide that management. And we're blessed in New Zealand to have a moderate amount of hydro storage. So again, Richard talked about using SDDP. There are many ways to kind of optimize power system operation, and we've been using dynamic programming for that. So I just want to give a little bit of background. Right, so just as a little bit of kind of basic background then, this is actually from work that Josh did. He did a fairly simple redispatch from the 2013 to 2015 years, with introducing more and more wind generation to replace thermal generation. So with this kind of knowledge that we're trying to decarbonise, then I guess some thermal generation was well, it was dispatched down, so it wasn't decommissioned, but was certainly used less. So you can see with that as we get more penetration along the bottom axis from the current situation through to 4,000 megawatts of wind generation, that it makes a huge difference to the amount. Reduced it down by, oh crikey, by nearly 90% for that 4,000 megawatts. Well, and with no additional storage in the network, then there is inevitably to be some energy spill, and from that simple model, there turned to be quite a lot of spill at the end from the wind generation, which makes the wind generation perhaps a little bit less economic. But the big question is with the thermal generation dropping down, then there is likely to be some decommissioning of some plant, which will be at the end of a lifetime. Can we survive without that thermal generation in place? Can we live without it? At the moment, thermal generation, it pays its way through energy. So this nearly 7 gigawatt-hours, that's how it funds itself. But what it's really doing is generating most of the time, keep water in our lakes to allow our hydro system to meet system peaks. So it has a secondary value there, which is not really recognized in the market, one would say. So when they stop it, appears, and we might be in trouble. So I guess on this pathway towards close to 100% renewable generation, we've got these questions to ask. Can we afford to decommission that thermal generation? Do we need it to be there just in case for those dry years? Can storage fill the gap? Of course, the value of storage comes from how well you manage the storage, and predicting how it's going to be managed in the future is fraught with assumptions. Will additional transmission capacity help? And Richard addressed that directly. And will we need additional generation capacity? And in fact, our reserve requirement is going to prove to be the limitation. So there's a few questions to ask about future power system operation. But one thing is for sure is that our storage management is going to be a key part of that. And it may be that additional storage actually might be the most effective way, maybe just by increasing lake level variation might be a very effective way to enable a more renewable intensive electricity sector. So in New Zealand, we've got constraints. We've got energy constraints at the moment. 80% of our power comes from renewable resources, and pretty much every puff of wind and every drop of water that falls in our catchments goes through and generates electricity. So any extra load above that is met by thermal. So 20% comes from thermal, and no amount of anything at the moment is going to make our utilisation of our current renewable resources any better. They're already good. Of course, we've got a very tight storage constraint. Only about 7% of New Zealand's annual electricity usage is stored in the dams. So actually, on an international stage, our storage is relatively tiny. In Brazil, they have 5 years storage. Here we've got a month and a half. Of course, transmission is another constraint as well, which the DC link plays a big part. Any kind of future scenario modelling is going to require redispatch of hydro generation to manage storage that is somewhere near the best that we could do. So I'm just going to spend a few minutes talking about this sort of modelling of hydro generation. Some of you in the room know this much better than me, in fact, but I'm for a more general. So any future scenario modelling, we need to optimise the hydro generation for that scenario. And that's a two-step process. The thing with storage is if you use it now, you don't have it to use in the future, which means there's a future cost from the decision now whether to use the water in the dam or whether to store it for the future. And so when you make a decision now, you have to factor in those future costs. So there's always a two-step process. The first is establish those future costs so that you can then use those costs to make the best decision now. And of course, the second step is once you have those future costs is to step through making your best decisions. I'm an engineer and I love verifying models. Verifying this sort of model is incredibly hard because we're looking at an optimal situation. And what is a measure of an optimal situation? Well, I guess no spill is partly optimal. And minimal use of expensive thermal generation. Is our current hydro system being operated optimally? Should it match an optimization? I don't really know either, but hopefully they're not too far out. But there's definitely some uncertainties with the sort of modelling about whether it really reflects what happens. Okay, so I just want to talk through the cost minimization process. Take a couple of minutes. So this is just for a single storage reservoir to keep it simple. We have storage level up to y-axis. So to establish those future costs, we go right to the end of our time horizon or even beyond what we're interested in. And we'll have various storage levels to which we can assign some values or costs. So if we have a very low hydro level, here we can use a bit of hydro, but some sort of I guess curve, or if you've got lots of water, it's kind of cheap. If you haven't got much, that forces thermal generation, it's kind of expensive. But the point is average one time, and then look forward, we can choose to rely on thermal generation, cost money now, but keeps us to a lower cost position. So balancing that cost is part of that optimization. We could release water and not use any thermal generation now, but we could so this step process is going through stepping back in time for a year or 2 years, really. 2 years is the minimum for a 1 year. Right, so there are some issues around this modelling which kind of make it a bit difficult. First of all, the number of storage locations that you have. I've drawn this graph with one of storage. But in fact, if I've got 2 reservoirs, then I've got 2 dimensions for that. I've got 3 reservoirs, I've got 3 possible dimensions. If we've got as many reservoirs as we have in New Zealand, there's lots and lots and lots of possible combinations of storage. And when we're making this dispatch decision of how much water we should use, how much thermal we should use, of course, another part of that is the inflows during that time period. And we don't know what those inflows will be in the future. So you've got to guess what those inflows are or use historical values. We've got 84 or 85 years of historical inflows. So you can use all of those and come up with a whole array of costs and then use some statistical measures to average those make it in a way that is suitable. So there's a question here about when you model what your risk profile is. So how optimistic or pessimistic are you going to be about future inflow? Forward time stepping for the district. Of course, we're modeling system sufficiency, which means we have to meet peaks, which means we have to meet half-hour demand peaks, so we know if there are going to be constraints. What that step size should be, and it's a little thing I want to dig into. Of course, whatever this does is not going to in the market. There's an awful lot of hedging that goes on. So thermal generators, for example, have committed customer base, and they will dispatch for that customer base, perhaps regardless of other needs in the network. And that's another requirement for the gen tailors, which is separate from the market optimization. So what I want to do is just talk about a very simple 2-node model and look at a hindcast. So look at what optimization does with the 2016 year of inflows and dispatch. So just a bit of background, we've got the South Island on the right-hand side, North Island on the left-hand side with a DC link between them. So we're keeping it very simple. What you'll see straight away is that the storage in the North Island is about quarter of the storage in the South Island. So the North Island storage is small, and similarly, the capacity is a lot less than the capacity of 3,300 megawatts in the South Island. So really, the North Island is the little brother of the South Island for hydro generation. Met, of course, that difference. And of course, most of the load is in the North Island as well. So, but there's a big difference in the storage capacity, and that's really scenario. Let me just check the time. So this is what happened in 2016. Just a few things to point out. First of all, we'll see the South Island storage. It's characterised by these upward blips and then sort of a steady downwards ramp. Those upward blips are inflow. It's been stormed, water's come through, and it's filled the dams. Our reservoirs are so small, they get filled up by. They really are small, and we depend on those rainfalls. It's not a steady rainfall. We can easily miss out on it. Then, of course, we've got the winter season where it's mostly falling a snow or not falling at all. And then we've got the spring thaws. There's quite a clear pattern which often gets replicated. Of course, this is the combination of inflows and dispatch as well. North Island Reservoir, honestly, it's kept at a pretty steady level through much of the year with a decline early in the season. I think mostly to do with inflows. So finishing values, kind of similar to starting values for that storage. So 2 examples. I should back up a little bit. What I want to do is just show the effect of what seems like a relatively trivial effect. The assumption is, well, the question is, when we're doing our price discovery, do we do price discovery with a half-hourly time step, same as the forward dispatch, or should we do it with a daily or longer time step, which is going to be a little bit different? So let's look at these. So maybe price discovery, first of all, quite well, a similar pattern. Info events are the same, and we've got this winter drop off in the lake level. The North Island generation is quite different. So a couple of things. First of all, that North Island drops down to 180 from 700. And look at it, it was run down to, in fact, 0 for a while. Why is that? I guess in the North Island, in the North Island, hydro is the cheapest generator. It doesn't have the HVDC link losses. It will always dispatch North Island hydro above everything else. So this constitutes a reasonably optimal solution. This storage in North Island is just a block on top of the South Island storage. So it's used first because it's cheapest. And it's used more. So it's used a lot more hydro. Likewise, the South Island generator uses more at that level come down. So there's a bit of a change there with what our optimal methodology looks like. Talk about that in a minute. With half-hourly price discovery, some weird things happen. First of all, the South Island lake level drops and the North Island lake level rises. Why is that? If you're doing half-hourly price discovery, times when there is full power being transmitted from the South Island to the North Island, and the HVDC link is the constraint. Actually, it's not the DC link, it's the reserves requirement for the DC link that constrains the power flow on the DC link. When that happens, of course, in the market, you get a high price in the North Island because there's load that's difficult to meet, and you get a low price in the South Island because there's stranded water. We'd like to generate, but we can't get it to the North Island. And with price discovery, when you get a high price in the North Island and a low price in the South Island, they propagate back in time to give us effectively higher water values, higher prices in the North Island and lower prices in the South Island at the time when that transmission constraint no longer exists. And that encourages more generation from the South Island in that pre-transmission constraint period and less from the North Island, resulting in these different lake levels. Could we allow transmission constraints to drive water storage decisions? Water storage is hugely about energy, not about I think that actually the right thing to do is to use a longer time period that misses out those peak transmission constraints. But when you look at it, we end up with anything storage, which looks better. Kind of tough to decide if your model is sensible or not. And I guess that's something that we're kind of seeing, is that this hindcast verification is very difficult to get, and quite small assumptions make quite a big difference. So here are the HVDC flows associated with that. And you can see that in practice, the HVDC flows are very granular, they're all over the place. And with our daily and half-hourly price discovery, firstly, there's a lot more happening. More. And we have these levels which are to do with our modeling with loss tranches. So it tends to dispatch to the maximum for a loss tranche. Right. What we'll see is we've got some southward flows there, which is always a bit confusing. So this is thermal generation in the North Island with our daily price discovery. Oh my goodness, let's look at this. First of all, we're dispatching base thermal generation all the time. That's keeping water in the lakes to meet those peaks. That's what that station should be doing. It's the cheapest thermal generation. And then we've got more expensive thermal generation, and then even more expensive thermal generation. So this is looking like it might not be that bad. The actual thermal generation is all over the place. It's kind of interesting here that the black line is the daily average, and these happening 4 times a month. They're weekend trips of thermal generation. So there's a bit of peak meeting with that thermal generation, but often that base generation is below its maximum, and it's then being replaced by expensive generation a little bit later on above its maximum. So why is that? I don't know. Have committed load through their hedge contracts and through their customers. So they are varying their offers and their expected generation all the time. Is that resulting in a suboptimal operation, a bit more CO2 emission than we could get away with? I don't know. You have to look at the situations more carefully, but it looks a bit different. And again, for that half-hourly price discovery, simply because there is more water coming from the South Island, more power coming from the South Island, less in the North Island, that's allowing us to get away generation. So it's just a little bit different. So the model for this sensitivity studies, but it's there ready to go. I think some key things with this modelling is that it's very quickly become computationally very intensive. So again, we talked about them being very, very number hungry programs. And it's difficult to capture that market participant behaviour because they have other drivers other than operational. And I understand that because there are commercial drivers that make their operations economic, which perhaps are not 100% consistent with minimum CO2 emission or minimum cost. Verification using hindcasts. If a previous year is not optimally operated, don't know if it is or isn't, can you expect there to be a match? With the simplifications and assumptions you make, should you expect a match? Do you want to even get a match? I'm not sure. So I think with these future scenarios, there's wisdom in many ways, and taking a consensus single model with an implicit assumption somewhere deep in the model or perhaps haven't tested. And of course, what these models do is that they will allow you to determine at least relative investment values, but it's that difference between investment costs, values and risks that will drive that investment's path, and that of course can be affected by government. So that's it. Perhaps I did mean to say something way back in that early slide, because we're all thinking about TY at the moment, and the TY energy is sitting around about 2/3 of that thermal generation. So if TY goes offline, and we were able to turn down thermal generation. Okay, that's all from me. Thank you.